Again, thank you so much for this opportunity to bring you some of our experience on the use of bamboo for different applications. Actually, we started this study or this area of research around 10 years ago, not more than that, in our group. And this is more or less the case in Brazil. We are not so dedicated to the study of bamboo as an engineered materials or for applications. And this is a shame because we see other countries like China and Colombia, that's a neighbor in South America. They are all very well developed using bamboo as a local resource and a very valuable material. And there is, at the moment in Brazil, a special line of research dedicated to supporting companies and research institutions to develop the concept of using bamboo as a material. So we always see bamboo as something that's there and we do not use. And for example, in Brazil, we can find the biggest natural forest of bamboo on Earth. So it's in Amazon region. And I have also visited a plantation of Bambusa vulgaris in the northeast part of Brazil, 50,000 hectares of Bambusa vulgaris, so it's an enormous plantation of bamboo. So we can also see the potential we have. So for the presentation today, we had 3 topics on cellulose production. That some of the studies I have already showed you before in my first presentation on Monday. The use of natural combs, let's say a more frugal application, and also some use for particle boards or for strands, a mixed kind of sandwich boards we are also studying in our group. So just a very brief overview about the use of the fiber itself. So we can extract from bamboo, and we see that's a smart material because the concentration of fibers, so that's the concentration of fibers in one of those, let's say, vascular bundles. Thank you so much. And then you can go, and this is actually a bundle of unitary cells. You can go deeper, and then you go to one unitary cell with the lumen inside, and we can go to the pulp, extracting the pulp from that area. So for producing paper making, or also for reinforcing uses. And we can go deeper if you fibrillate those, let's say, fibrils. You can go in a smaller scale, in the nano scale, as a reinforcement. So this is the pulp. We use the organosolv pulp. That's ethanol water. Brazil is a big producer of ethanol, so for us it's easier, but we still use almost 100% of our chemical pulp is kraft pulp. And this is economically very competitive. The cost of production of kraft pulp is very low, and so economically speaking, kraft pulp has a huge competitiveness in the market. So this would be in a much smaller scale. So that's why we were thinking about having some organosolv, and then of course you can use lignin taken from this pulping process. So that would be some attractiveness depending on the scale of production and depending on the market for using those fibers coming from bamboo in Brazilian market. So this is just a laboratory scale of refining. This is, of course, it's an energy intensive process. So this is something, a drawback in the production of this nanocellulose material, because this is intensive in energy. So we should thinking how to optimize this production, but one possibility is also using less. So as we are using this grinding process to nanofibrillate the fibers, we are also looking for less use of fiber, and then of course we are also optimizing the application of the resources. And as I showed you before, if we combine the pulp with the nanofibers, we can of course have this multi-scale reinforcement and get to much higher, let's say, performance, mechanical performance. But of course, when I say this, I try to use all the knowledge the industry already has. For example, this procedure of production is a kind of mimics of what happens in the real scale, where we use pulp. We need a lot of water for dispersion, for mixing, for, let's say, a good homogenize the composite itself. But in the end, for this kind of inorganic binder, we need to have the smallest amount of water possible in the final product. So we drainage the excess of water, and that's what we try to do in the lab, trying to reproduce what they are doing in the real scale in the industry. So we had to modify a little bit also the side of the matrix to get all the potential of the pulp, and also from the nanofibrillated materials. We have to modify, for example, the carbonation I told you about is something refining the porosity and then making this porosity compatible with the nano-reinforcement. Otherwise, the nano-reinforcement will be losing inside of that big amount of porous. Just to have an idea, these products, they have up to 35% of the porosity inside. And I don't know if it's, you can see very well, but in here you have a micro structure, a micrograph of the composite and the fiber, let's say the pulp fiber, and this fuzzy part of the picture is the nano structure, or I mean the nanofibrillated cellulose. And what it's doing here, it's improving the interface, it's modifying the interface between the fiber and the matrix. For example, in the case of your study, you could use the nanofiber as one of the, let's say, of the tools to modify the interface between the wood and the wood particles and the gel polymer. So making the bridge between the two phases and modifying the interface between the two phases. So it can help improving the mechanical behavior. So another application is for filtering media. So what we had this study for electrospin process applied using some recovered polymers. In this particular case, we used PET, recovered, recycled PET, for producing those mats for filtering. But one problem they were facing with those mats was regarding the mechanical strength of the mats. So the idea in this case was to improve the quality, the mechanical performance, using or bamboo or other reinforcing elements in the nanoscale to make these filtering elements, let's say, more competitive with other alternatives, such as glass mats or made from basalt or from other types of inorganic fibers. So in this case, we had a spin process that could align the fibers, and the cellulose or the lignin was dispersed with the polymer to trying to reinforce those polymers, and we did test if that could interfere in the alignment of the fibers, but it didn't. But it could have a very nice, let's say, improvement in the tensile, in the direct tensile strength, using that cellulose extracted from bamboo or other non-wood resources like sisal, and using the cellulose, we see that comparing to PET in the preferential alignment or in the perpendicular alignment, we see that, of course, in the direction of the fibers, this can be very helpful, even doubling the performance of tensile strength. So those natural resources can improve the performance, the mechanical performance. Now we are working in the filtering aspects, in the porosity of those mats, to see which size or which type of elements could be captured in that types of mats. For example, for air conditioning systems, for hospitals or for other public environments where you have to take care of the quality of the air, you have to be aware also about not only strength, but also the quality of the retention or the capture of the elements in the air. So this is to show that even in the micro or in the nano scale, you can use those fibers in very specific applications for filtering or for reinforcement, depending on the expectations you have for that type of use. But going now to the other extreme, to the use of bamboo as a natural pole, the first thing we have to have a look in our specific case of tropical countries, but I think in here wouldn't be different, is the treatment against natural degradation. So this is a particular case. It's a kind of beetle that can make a big, let's say, degradation of the material after just few months. So you can use for temporary construction, but for permanent construction it would be a disaster using a bamboo culm, for example, because the degradation is very fast, especially in humid or in high temperature environments. So the idea of this study, it's still ongoing, this study, is a doctorate student. He is studying how to make a treatment. Of course, we know a lot of different treatments for wood and also for bamboo that are conventionally used, but we know some of them, they have some restrictions. In many places they are not allowed anymore because of the contamination or the accumulation of those types of treatments. At the moment, he is studying those two in red, circled in red, tannin and citric acid for chemical modification or in situ polymerization inside of the bamboo, the vessels. And that's the initial, thank you, the initial part of the study using the conventional treatment, the CCB, as a, let's say, is still allowed to use this in Brazil, and this is just as a reference in the study to compare the treatments we are proposing for those bamboo poles. And those are the equipments we have in our lab. for treating, and to see how, as a quality control, to see how this treatment interacts with the bamboo. And in this particular case, we see that there is an accumulation of those CCB treatments in the vessel of the fibers. I don't know if it's difficult to see from here, but what's red is copper and what's yellow is chrome, and there is an accumulation of those two elements in the vessels of the structure, of the lignocellulosic structure. And you can also see here in this EDS that in the case of number 1, that's the vessel part. It's not so easy to read, but number 1 is the vessel part of the structure. We see that there is an accumulation of both chromium and copper. So we expect that the treatment goes preferably in this part of the structure of the wood or of the bamboo, and this is nice because in many cases those agents, biological and that goes attacking the material, they would use those vessels as the roots to invade the structure of the material. So that was the idea. And also in this slide we can see how, for example, in the case of citric acid or in the case of the disodium octoborate tetrahydride, they act over the material, modifying the structure of the bamboo. Let's say how the citric acid can interfere and can be, let's say, fixed in the structure of the wood or in the structure of bamboo. And in this particular case, the reference are the squares over there. If you just use the boron, you are almost the same. It's not avoiding any, let's say, absorption of the water. The absorption of the water will be almost the same. But if we combine the acid, citric acid with boron in that percentage, for example, you can have a considerable reduction of the water. Thank you. Absorption. And in
left middle. Center scale.
This one. Sorry. This one.
Yeah.
Thank you. And in here we can see the C double linkage with oxygen. That's the modification in the structure of the wood that can explain or help us to explain why this is happening in this case, how we are achieving this reduction of water absorption using, in this case, the citric acid. So this is part of that study as well. I'm sorry. I think I was too fast. Sorry. Yes. Okay. So now, this I study in collaboration with Pittsburgh, where Christian, this student, was to stay for 6 months or 5 months, and in there he went to see the mechanical characterization of the materials and how those treatments would interfere in the mechanical behavior of those materials. So is this citric acid treatment or octoborate treatment interfering in the mechanical performance of those materials, because we don't even know how is the mechanical performance of bamboo under different types of, let's say, loading. So we can see here compression, shear, bending, tension, and with the interference of the node or without the interference of the node, and we can compare the different types of strength with the modulus corresponding to which kind of loading. So just taking one example, this case, for example, this is for tension, for direct tension, this is the blue. Then we see that the behavior is very interesting. So we can have for direct tension in the case of bamboo, no matter if it's treated or not treated. Of course, there is a standard deviation here, but it can go up to 250 megapascals of direct tensile and also around 18 gigapascals for the modulus of elasticity. So we could have an idea and even of the Poisson modulus of that material for what is important for design, using bamboo for the design. And in here we see the interference of different types of treatments, the conventional or non-conventional treatment, that the material stays stable. There is no much difference between, for example, in a bending test, in modulus of rupture or modulus of elasticity, there is no much change in the behavior of the material depending if it's A, B, or C, or always working in this case in the internode part of the material. So this is a kind of study that could give us more support for standardization or even for designing using that material. If we talk about bending, now it's showing in there how it performs, the concentration of tensions, because we are following the displacement and correlating the displacement with the tension. We can see how the material behaves and how is the concentration or how the neutral line moves during the bending test. And of course it will vary, it can vary not only using different treatments as I said, but also can vary depending on the species of bamboo or if it's densified or not, treated or not. So there are many variables we are trying to understand how it works. And moving to another type of studies, just very briefly, those engineered bamboo, not using the bamboo poles, but using the particles or using the strands made of bamboo. So this study we are using a formaldehyde-free glue. That's a polyurethane resin based in castor oil that's available there in Brazilian market. So we try to see how it works in OSB panels produced with strands of bamboo. So that's another doctorate study using this pressing, thermal pressing, and the results were quite optimistic, promising, because comparing with European standards for that, 650 kilograms per cubic meter of density and different fractions, different amounts of resins from 8 to 15%, we can follow how is the water absorption, thickness, swelling, of course reducing drastically with higher content of resin. But of course, as was said before in the frugal innovation, sometimes we don't need, for some applications, to have water absorption so low. So in many cases, it's acceptable to have some water absorption, especially if it will work in an envelope or in internal application. So depending on the application or depending on the standards requirement, we can work on different types of performance. And taking a look in the mechanical characterization under bending as well. So we see also that it's possible, even the 8% resin could be compatible with the requirements, let's say, or most of the requirements of this OSB type 1 panels from the EN standard. So it can be possible to find a, let's say, a market niche for those products. Going in another, now we are presenting here another doctorate study, and this she just started less than 1 year ago. She started working the densification of bamboo. So that's nice because you can see the effect of moisture content, the starting moisture content of bamboo, comparing the undensified bamboo until the final steps of densification from 0 to 20% of moisture content. So 0% you see a lot of cracks, and then if you manage to have an adequate moisture content during pressing, you can accept a lot of compression. And she also divided the bamboo in streams or in layers. So the external layer, where you see a higher concentration of fibers, in a medium layer and internal layer, how they behave separately, depending on the position of where you are. And in this study, I think I'm afraid to touch again because maybe it's too heavy. It's taking a while to move. But this we have a lot of knowledge on that regarding to wood, but not that much referring to. Now it's okay. Referring to bamboo, especially in Brazil, as I said. And we see in all the cases, internal layer, middle layer, or outer layer, we can see a considerable improvement in the performance. We can see here the undensified and densified material about the apparent density or bulk density, how it is the change in the density, and how is the improvement, of course, from 0 to 20%, how is the improvement of the performance, of the mechanical performance of this densified bamboo. So there is a great potential for this material in types of, you see the performance is very nice. You can achieve up to 300 megapascals in modulus of rupture, which even for wood, I think it's a good performance. So it's a material that can be really used for several different applications. And then after that, she started, or she's a very, let's say, hard-working student. She came to now to another step that's flattening the boards, the cones, to produce the strips that will be part of the sandwich panels. I mean, the external part of the sandwich panels. So if we see, as I showed before, the performance is very nice. We are not just improving the stress, but we are changing the way, the modulus of elasticity as well is improving a lot because of this pressing. And after she combined this with the particles for the internal part of the board. So those are the, let's say, the processing steps. Of course, all of those steps were just in our lab, so it could be much optimized because of the industrial scale. And that's the idea, to use a glue, a PVA glue, for joining all these three, let's say, layers. The two external layers of strand and the internal layer of particle boards, everything made of bamboo, of course, in this particular case. So this can be for the future another good application. So we see a great potential for this, and we are at the moment looking for collaboration with the industry, because as I said, the Brazilian government has dedicated some money, so that put available some money for this collaboration between the industry and the research institutions to have something transferred to the market. And this is our future plan, to have a small building using those treated bamboo poles in our campus, in our farm there. We have the bamboo, that's I think it's a Dendrocalamus giganteus, and we also have the treatment space for producing a kind of, let's say, a very simple infrastructure produced of bamboo, so people can realize, people can trust, they can see, because it's not usual there to use bamboo for buildings until now, unfortunately. So again, thank you so much for your time and your attention.
I do have a question, obviously.
Yes, please.
Two, actually. First of all, you mentioned the resin contents in the beginning when you talked about the QR bonds OSB. Was that a solid content, or do you remember